Moving thousands of megawatts of electricity across continents is a delicate balancing act. The global power grid relies entirely on specific, localized nodes to maintain voltage pressure and prevent the system from collapsing into cascading failures. Without constant voltage translation at these junctures, industrial motors stall, commercial servers shut down, and mass transit grinds to a halt. Every layer of modern infrastructure relies on the unbroken operation of these devices. To maintain this stability, the industry relies on strict, formalized engineering guidelines that govern the design and deployment of this technology across all sectors. The standard reference is IEC 60076-1. It dictates that a transformer is a static piece of apparatus with two or more windings, operating entirely through electromagnetic induction. Its specific mechanical purpose is transferring energy between systems. It takes a system of alternating voltage and current and translates it into another system with different values, while strictly maintaining the original input frequency. Whether a unit is managing a localized 50 kilovolt ampere load or routing 1,000 megavolt amperes across a state line, the underlying physics and the industrial definition of the machine remain completely invariant. Translating that electrical power from a central generation plant all the way down to a household requires passing the current through multiple stages of extreme physical scale. High-voltage industrial translation and bulk power transmission require massive structural footprints. These primary nodes must safely manage and route lethal amounts of energy. Compare those high-voltage giants with the end-stage delivery systems designed for residential areas and public streets. Woven directly into residential infrastructure, these units maintain a highly localized, suspended footprint, operating within meters of the public. This extreme visual disparity, from towering cylinders to small pole-mounted canisters, is purely a manufacturing adaptation to location and thermal limits. It represents zero shift in the underlying electromagnetic physics. The primary constraint of transformer engineering is building a static, high-voltage induction machine using only 4 foundational material groups. First, the core, thin plates of magnetic silicon steel stacked to minimize energy loss. Second, conductors, thick copper coils providing pathways for current. Third, solid insulation, dense paper separating windings from the core. Finally, dielectric fluid. The assembly is submerged in mineral oil. From a neighborhood utility pole to a cross-country transmission substation, no other fundamental components are required to execute the physics of the system. The entire history of transformer engineering is simply the refinement and optimization of these 4 materials to survive intense thermal and magnetic limits. Each material plays a highly specific physical role. The silicon steel is stacked to efficiently generate and channel a concentrated magnetic field without wasting energy as heat. The precise geometry of the wrapped copper coils determines how they intersect with that magnetic field, successfully inducing a new current inside the secondary winding. Pushing current through the resistance of the windings and forcing magnetic flux through the core generates an intense catastrophic thermal load. To prevent the system from destroying itself, the cellulose and the dielectric fluid work in tandem. They suppress high-voltage electrical arcing while rapidly absorbing and dissipating the internal heat. This dynamic turns transformer design into a spatial geometry problem. Engineers must maximize the magnetic flux interacting with the coils, while leaving enough physical space for thermal cooling and electrical insulation. To solve that geometry problem, manufacturers bifurcated transformer design into 2 distinct architectural topologies, the core type and the shell type. In the first and most common topology, the core type architecture, the copper windings enclose the magnetic core. This configuration typically utilizes a standard vertical axis orientation for the core legs, allowing flux to travel cleanly up and down the pillars. The primary mechanical benefit of the core-type layout is factory efficiency. It is considerably easier to mechanically wind the copper coils directly onto the accessible core legs. Because of this manufacturing advantage, this specific topology is the globally dominant paradigm, serving as the standard for major manufacturers like ABB. Core-type architecture perfectly balances electromagnetic efficiency with a streamlined, highly repeatable assembly process. However, severe spatial constraints in certain industrial applications require the alternative architectural solution, the shell-type transformer. This is the structural inverse of the core type. Here, the metallic core encloses the copper windings, physically shielding them from the outside. By encasing the windings, this architecture allows for either a vertical or a horizontal axis orientation, accommodating tight clearance constraints. Building it requires a complex assembly process. The factory must pre-form the heavy copper coils and then intricately build the steel core around them, piece by piece. This structural difference has zero impact on the operational physics or the service reliability of the unit. The induction process remains identical. The division between core and shell proves that architecture is dictated entirely by factory tooling, shipping weight, and physical space limits, not by Faraday's law of induction. A common colloquialism divides the market into two distinct categories: power transformers and distribution transformers. The industry shorthand assumes a power transformer is a massive multi-ton unit used exclusively for high-voltage transmission on the macrogrid. Conversely, it assumes a distribution transformer is a small, low-voltage unit dedicated to end-user delivery. But the strict truth is that IEC engineering standards do not recognize a physical, structural, or physical difference between these two terms. They are all technically power transformers. Every single unit is executing the exact same core or shell type induction using the exact same form materials. Mislabeling units based on where they sit on the grid creates false assumptions about their internal physics. To accurately categorize these machines, the taxonomy must be based strictly on their mathematical scale. This chart maps out a rating-based taxonomy beginning at the highest tier of the distribution network. The large distribution class handles extreme metrics, rated over 10 megavolt amperes, stepping down primary voltages of up to 72.5 kilovolts. Pushing that volume of power generates a severe thermal load. Cooling the dielectric fluid requires separate, massive external radiators bolted directly to the tank walls. Moving down the rating scale brings us to the local grid nodes. The medium or substation class metrics drop from 10 megavolt amperes down to 112.5 kilovolt amperes, handling up to 36 kilovolts. There is a direct physical correlation. As the megavolt ampere rating drops, the internal thermal load decreases, and the external cooling footprint naturally contracts to match it. Finally, at the smallest tier of the network, we find the pad-mounted class, operating directly in public-facing environments. Handling 75 to 5,000 kilovolt amperes and voltages up to 34.5 kilovolts, these units require specialized safety enclosures to isolate the active terminals. Because the thermal load is comparatively low, external radiators are entirely replaced by corrugated tank walls to dissipate heat, while the locked enclosures protect passing pedestrians. But beneath the corrugated steel and heavy safety locks, the same silicon, copper, cellulose, and oil are doing the work. The fundamental physics of induction are completely indifferent to the size, the application, or the shape of the external box. True engineering mastery isn't inventing new physics for every problem. It lies in manipulating four invariant materials into a flawlessly scalable global architecture.